A central question is whether filters need to be prescribed with accuracy. The evidence indicates that, for a proportion of individuals, specific spectral filters can produce substantial and measurable effects on visual comfort, reading fluency, or symptom reduction. However, the challenge lies not in the potential value of filters, but in the methods traditionally used to determine them. Current approaches to filter assessment have significant methodological limitations. Trial and error selection is often presented as a pragmatic solution, yet it lacks control, repeatability, and objective criteria. Its apparent simplicity obscures the fact that it is highly susceptible to expectation effects, inconsistent sampling, and practitioner bias. Similarly, sampling conducted by optical professionals, while well-intentioned, faces structural constraints. The available filter sets are typically sparse, unevenly distributed across the color space, and restricted by commercial or practical considerations. As a result, the sampling process cannot adequately explore the full range of potentially beneficial chromaticities. This makes it unlikely that the chosen filter represents an optimal or even near-optimal solution. Empirical prescribing based on overlays, tints, or subjective matching by eye introduces further limitations. These methods rely heavily on conscious preference judgments, which do not reliably correlate with functional outcomes. They also fail to account for subtle interactions between luminance, chromaticity, and individual neural responses. Consequently, prescriptions derived from these procedures are unlikely to achieve maximal effect. To address these issues, we have developed a method designed to circumvent the inherent weaknesses of existing approaches. This system, known as the read eye, provides a structured, objective, and reproducible means of identifying filter characteristics. It eliminates reliance on subjective matching, avoids the constraints of limited sampling sets, and replaces trial and error with a systematic procedure grounded in measurable responses. The read eye therefore offers a pathway to more accurate, evidence-aligned filter prescription. By the early 20th century it had become clear that color matching posed a fundamental problem for science and industry. Different observers produced inconsistent matches, and different light sources or media altered the perceived chromaticity. This variability made it impossible to specify colors reliably across laboratories, manufacturers, or countries. As a result, extensive international research was undertaken to establish a system capable of defining color in a consistent, reproducible, and observer-independent manner. This work culminated in the development of the CIE 1931 color space, the first internationally agreed framework for quantifying color. It provided a mathematically defined, device-independent coordinate system based on standardized human observer functions. For the first time, colors could be specified accurately, communicated unambiguously, and reproduced with predictable fidelity. The read eye method is unique in that it anchors all of its measurements and outputs directly to this international color standard. By referencing filter effects, chromaticities, and individual responses to the CIE 1931 space, the system avoids the ambiguities inherent in subjective matching or limited sampling sets. This ensures that the filters identified are not only internally consistent but also precisely located within a globally recognized color coordinate system. In doing so, the read eye provides a level of accuracy, reproducibility, and scientific transparency that earlier prescribing methods cannot achieve. Let me now introduce the read eye. It is a professional standard instrument designed to enable the precise prescribing of tints with reference to internationally recognized color metrics. Unlike traditional approaches, which rely on subjective matching or limited sampling sets, the read eye operates entirely within the CIE 1931 color space. This ensures that every prescribed chromaticity is defined, reproducible, and comparable across laboratories, manufacturers, and lighting environments. The system incorporates the full complexity of tint design, including spectral transmission characteristics, luminance effects, and the interaction between filter chromaticity and the illuminant. By integrating these variables, the read-eye provides prescriptions that remain stable and accurate under real-world lighting conditions rather than only under the specific conditions of assessment. Through this combination of objective measurement, international color standardization, and controlled evaluation, the read-eye establishes a level of precision that has not been achievable with earlier methods. For this reason, it functions as the gold standard for tint prescribing, offering a systematic and scientifically grounded alternative to empirical or trial and error approaches. The read-eye is unique and innovative. It works using the principle of univariance. The principle of univariance states that once a photoreceptor has absorbed a photon, its electrical response depends only on the number of photons absorbed, not on the wavelength of those photons. In other words, a receptor cannot distinguish why it responded, only how much it responded. This is a foundational concept in color science. A useful way to explain this is through the analogy of a television screen. A TV creates millions of colors using only three primaries: red, green, blue. Each pixel does not know the wavelength of light it emits, it only produces a certain intensity of each primary. By adjusting the intensities of the three primaries, the TV can reproduce virtually any color within its gamut. The viewer's visual system interprets these intensity combinations as specific colors, even though the underlying wavelengths are limited. This works because the human visual system itself is based on univariance. Each cone type signals only the amount of light absorbed, not the wavelength. The brain reconstructs color from the relative responses of the three cone classes. How the read-eye uses univariance. The read-eye applies the same principle in a controlled, professional standard instrument. Because photoreceptors respond only to absorbed intensity, the read-eye can mathematically combine the spectral effects of any tint with the spectral characteristics of any illuminant. Compute the resulting cone excitations precisely. Reproduce the perceived effect of that tint-light combination without physically needing the tint or the light source. This allows the read-eye to simulate daylight at different correlated color temperatures, indoor lighting conditions, complex spectral tints, interactions between tint and illuminant that would be impractical to test physically. Just as a television can generate a vast range of colors from three primaries, the read-eye can generate a vast range of tint lighting combinations from controlled, calibrated primaries, because univariance guarantees that the visual system responds only to the pattern of cone excitations, not to the physical wavelengths that produced them. The read-eye operates directly within a defined, reproducible color space. It measures and compares stimuli in a calibrated color space, that is CIE 1931 or derivative spaces. This avoids the usual hand-waving about tints and instead grounds everything in measurable chromaticity and luminance. It means two filters can be compared quantitatively, not subjectively. It optimizes filter selection by modeling the interaction between the spectral power distribution of the ambient light, the spectral transmission of each filter, the user's own visual response profile. This is the bit most systems ignore. Lighting conditions change the effective chromaticity of the world. Read-eye accounts for that rather than pretending daylight, LED, and fluorescent are interchangeable. It provides a consistent basis for comparison. Because everything is expressed in the same color space, you can compare filters under different illuminants. Predict performance before trial. Avoid the try this and see empirical nonsense you and I both dislike. And it makes the choice of filter computable, not anecdotal. This is the real innovation. Read-I turns tint selection into a reproducible optimization problem rather than a subjective guessing game. The Read-I is a computer-controlled projection system that delivers calibrated, spectrally defined light onto a lectern surface. This provides a stable and reproducible color stimulus against which filters can be assessed. By controlling illuminant type, intensity, and chromaticity, the system enables objective comparison of filter performance under standardized or user-specific lighting conditions. The Read-I operates through a sequence of predefined templates that guide the assessment process. When the user enters the subject's identifiers, the system queries its database to determine whether a previous assessment exists. If a match is found, the system can reproduce the earlier test conditions and outputs, enabling precise comparison between current and historical results. On the initial assessment screen, the operator has access to a range of stimulus control tools. These include an RGB sliding system for manual color mixing, a dimming control for adjusting luminance, a library of preset colors, and fields for entering precise CIE chromaticity coordinates. Together, these allow the user to define the projected light stimulus with both intuitive and scientifically calibrated methods. The fine-tuning screen enables the operator to determine tolerances and define the effective gamut of the system. This capability is critical when assessing performance under multiple illuminants, as it allows the software to identify and eliminate metameric failure and to separate changes in brightness from changes in saturation. The 6-point gamut is constructed from vectors within color space, providing a structured and reproducible framework for evaluating filter behavior. No other system offers this level of chromatic precision or control. This makes the scientific logic explicit. Tolerances? Define how close a stimulus must be to a target before it is considered equivalent. It works to 1 McAdams ellipse and 0.01 in XY coordinates. Gamut size determines the operational boundaries of the system, the region of color space within which comparisons are valid. Multi-light assessment allows the same filter to be evaluated under different illuminants without ambiguity. Metameric failure detection. The system can identify when two stimuli match under one light but diverge under another, something most systems cannot even measure, let alone control. Brightness versus saturation differentiation. A major weakness in other systems. Read-I can separate luminance changes from chromatic changes, preventing false positives. 6-point gamut based on vectors. This is a strong, defensible engineering statement. 6 anchor points, each defining a vector, forming a controlled, navigable region of color space. The final stage allows precise selection of the tint used in the projected lighting. Because the same tint can produce dramatically different effects under different illuminants, the system evaluates tint behavior across lighting conditions. This prevents the two major failure modes seen in other systems, a tint that produces no meaningful effect, or one that generates an unpleasant or counterproductive response. By modeling tint-illuminant interactions, the Read-I ensures that the chosen tint performs consistently and comfortably in real-world environments. The Read-I includes a self-calibration module that ensures the projected stimulus remains spectrally accurate over time. The system can also analyze and verify the transmission characteristics of lenses, allowing them to be stored as reference profiles. New lenses and lighting types can be added to the database at any time, enabling the system to expand as technology evolves. A separate video will cover the testing techniques in detail and demonstrate how these capabilities can be applied in practice.